Hello everyone, today let's take a look at QP 118, another Poisson question. So on a given busy intersection, the probability of at least one car crash in a 1 hour time interval is 8/9. So assume that car crashes occur independently of one another and at a constant rate throughout time. Now in part A, it's asking us to find the probability of at least one car crash in a 30-minute interval. So first of all, what do we know? Well, we know that we have a 1 hour time interval, which I'll draw like this. And we know that in this 1 hour time interval, the probability of at least one car crash occurring, so I'll say the probability that x is greater than or equal to 1 is equal to 8/9. Okay, so x is the number of car crashes in an hour. The probability that it's greater than or equal to 1 is 8/9. And this is our 1 hour time period right here, which we can obviously break down into two 30-minute time intervals. So the easiest way to solve this problem is just to realize that we have the probability that x is greater than or equal to 1 here. So we can just take 1 minus that probability, the probability that x is greater than or equal to 1, and that'll just be equal to the probability that we have no car crashes within an hour. So 1 minus 8/9 is just going to be equal to 1/9, obviously. So that is the probability that we have 0 car crashes in 1 hour is 1/9. So now that we know this, we can basically realize that the probability that we don't observe a car in this first 30-minute interval is going to be exactly the same as the probability that we don't observe a car in the second 30-minute interval, because we have these independent car crashes that occur at a constant rate throughout time. So first of all, the constant rate tells us that this probability right here for this 30-minute interval of 0 crashes in here is going to be the same as the probability in this 30-minute time interval over here. So I'll call those both P. Now, since these car crashes occur independently of one another, we know that the probability of 0 crashes in this first time interval, we can just multiply that by the probability of 0 car crashes in the second time interval, and that'll be equal to the probability of 0 car crashes in our whole 1 hour time interval. So all I have to do is set p squared equal to 1/9, and then we can solve for p. P is just going to be equal to plus or minus 1/3, but in this case, only 1/3 makes sense. Now, this is the probability of 0 car crashes in a 30-minute time interval, so the probability of at least one car crash in a 30-minute time interval is just going to be 1 minus 1/3, which is just equal to 2/3. Okay, so one more time, because we split our time interval into two equally sized different chunks, right? They're both 30 minutes and car crashes occur at a constant rate throughout time. That means that the probability of any number of car crashes occurring in this time interval is equal to the probability of any number occurring in this one. And because we know the probability of 0 car crashes occurring in the entire time interval, well, that's just going to be equal to the probability of 0 car crashes occurring in the first time interval times the probability of 0 car crashes occurring in the second time interval, because they happen independently. So we use that to solve for the probability of 0 car crashes occurring within a specific 30-minute time interval, and then we subtracted that from 1 to get the probability of at least one car crash occurring within a 30-minute time interval. So that's the answer for part A. The answer for part A is 2/3, not 1/3. I don't know, I have 1/3 circled. Okay, so now for part B, we want to find the expected number of car crashes in a 1 hour time interval. We know that any number of car crashes can occur within a time interval, so we have anything from x equals 0 all the way up to infinity of x times the probability that x is equal to that value. And the question tells us that the probability that x is greater than or equal to 1, well, we know that's 8/9, so we know the probability that x is equal to 0 was equal to 1/9, remember? But it doesn't give us any more information about how these probabilities actually break down. We know the probability that x is equal to 0, but we don't know the probability that x is equal to 1 or the probability that x is equal to 2. All we know is the probability that x is greater than or equal to 1, which doesn't tell us a whole lot to solve this. What we do know is that car crashes occur independently and at a constant rate throughout time. So if we just did QP1, we know that this is basically a Poisson process. And you remember in QP1, we derived the PDF of the Poisson distribution from basically the expected value of x. So now we kind of need to reverse engineer the expected value of x from basically some information about the distribution. We know that in this 1 hour period, we have some expected number of car crashes to occur. We know that we can break this 1 hour subinterval into a bunch of infinitesimally sized little tiny subintervals, such that when we are in one of these subintervals, we know that either a car is going to come or it's not. So we know that if we break this hour into n equally sized of these infinitesimally small subintervals, just like we did in QP number 1, right? We know that the expected value of x is just going to be the expected value of the sum of all of these indicators. The expected value of any indicator is just equal to the probability that a car comes within that subinterval. So the probability of a car coming in any of these subintervals is just going to be the expected value of x divided by the total number of subintervals that we have, n. That's the probability of a car coming within one of those subintervals. So we know that 1 1 minus the expected value of x divided by n will be the probability of 0 cars coming within that subinterval. We know that since all of these subintervals are independent and occurring at a constant rate, we can just multiply them, and that will multiply to the total probability of 0 cars coming within the hour, just like it did up here. So I have n different subintervals, each with this probability of 0 cars coming within that subinterval, right? So I take this to the power of n, and I know that's going to be equal to 1/9 when I send n to infinity. We can just take this limit right here, standard limit, it's just going to be e to the power of negative the expected value of x. That's going to be equal to 1/9, and we can solve for the expected value of x just by taking the natural log of both sides. So we know that the negative expected value of x is equal to the natural log of 1/9. So laws of logs, the natural log of 1/9 is just equal to basically the negative natural log of 9. We multiply both of these sides by -1, and we get that the expected value of x is just equal to the natural log of 9. Also, in doing this, we basically just rederive the Poisson for no reason. You could have also just known that this is basically going to follow a Poisson PDF because we have independent events occurring at a constant rate throughout time. So instead, we could have just realized that this right here is the probability distribution where lambda represents the expected number of events to happen, or car crashes in this case, within an hour. And since we know that the probability that x is equal to 0 is 1/9, well, if we plug in x equals 0 into this equation right here, we just get e to the negative lambda times lambda to the power of x. In this case, x is 0, so this would be 1 here, and then this would be 1 on the bottom as well. And from that, you'd get the fact that e to the negative lambda is just equal to 1/9, and again, you solve for lambda, you get lambda is equal to the natural log of 9. So for any given hour, we expect that the natural log of 9 car crashes occur. So the expected value of x is the natural log of 9. Now let's go on to part C. Okay, so in part C, we need to find the probability that at most one car crash occurs in a 2-hour time interval. We know that basically if we let x be the number of car crashes that occur in a 1-hour period, the expected value of x is the natural log of 9. We just showed that in part B. We were dealing with a 1-hour interval before. We know that the expected number to come within this interval right here is going to be the natural log of 9. Now also, this is also going to be an hour, obviously, so the expected number of car crashes in here is also going to be the natural log of 9. So the expected number of car crashes to occur within this whole 2-hour interval is obviously just going to be the natural log of 9 plus the natural log of 9, which is going to be 2 times the natural log of 9. We know that because our events are occurring at a constant rate throughout time. Now in this 2-hour period, this is also going to be basically a Poisson process. So let's just look at this whole 2-hour period. The expected number of cars to come within here are going to be 2 times the natural log of 9. Now we need to find the probability that at most one car crash occurs in a 2-hour time interval. Okay, so more formally, if we let y be the number of car crashes in a 2-hour period, then the expected value of y is 2 times the natural log of 9. We can also rewrite this just by natural log rules. We know that this is equal to the natural log of 9 squared, which is 81, right? So let's just simplify. Now I'm not going to rederive the formula for the Poisson distribution, but we basically know that this will follow a Poisson distribution. So the probability that y is equal to little y is just going to be e to the power of ln of 81, actually the negative power of ln of 81 times ln of 81 to the power of y divided by y factorial. We want the probability that at most one car crash occurs within a 2-hour time interval. So the probability that y is less than or equal to 1, basically, which is just equal to the probability that y equals 0 plus the probability that y equals 1. So now if we plug in 0 to our equation up here, we're going to get this one will be a term of 1, and so will this one. So we'll just get that the probability that y equals 0 is just equal to e to the power of the negative natural log of 81. So if we have a negative log, we can just rewrite that as basically the log of 1 over the number inside. So the natural log of 1 over 81, e to the power of the natural log of e of 1 over 81 is just equal to 1 out of 81. Could have also got that just by realizing that the probability of no car crashes occurring within an hour is 1/9, same over here, and we can just multiply those together, right, to get 1 out of 81, just like we did in part A, but this is using the Poisson PDF formula. Now, what's the probability that y is equal to 1? Well, now we can just plug 1 into this equation up here, and what do we get? Well, we're going to get a 1 on the bottom. This is still going to be 1, and we're going to get an extra ln of 81 out front. So this is just going to be equal to 1 out of 81 times the natural log of 81. So when we add these up, we just get 1 plus the natural log of 81 divided by 81. So that's our final answer, which is roughly equal to about 0.066. So that's roughly 6%, which makes a lot of sense because basically the natural log of 81, the expected number of cars to come within 2 hours, is somewhere around the lines of 4.3. So the odds of us getting 0 or 1 car crashes within this 2-hour period, if we expect 4 every 2-hour period, is going to be pretty low, which we got 6.6%. So yeah, just some Poisson questions here. Basically, you know that when we have some type of event occurring independently of other events and at a constant rate throughout time, it's basically a Poisson process.